Hello there, and welcome to another quiet night with the Sleepless Scientist. Tonight, we'll wander into a story that begins not in the depths of the cosmos, but much closer, just behind your eyes. If you enjoy these calm explorations, a like or subscribe would be a gentle gift. It helps more sleepy travellers find their way here. And if you feel like sharing, let me know where in the world you are and what time it is. It always feels like a constellation of windows glowing across the world, each of us pausing together in the same moment. Now soften the room, let a hum keep you company, and let's begin. And if you drift off along the way, that's more than fine. When you open your eyes, it feels as though you're seeing the world directly, as if vision were a clean window. A tree is simply there. The kettle on the stove is waiting. The cat is staring with quiet judgment. Yet what you actually see is not the world in raw form, but a careful blend. Your brain holds on to images for as long as 15 seconds, weaving them together into a continuous story. Without this, the world would jitter and flicker, each blink or quick eye movement breaking the flow. Instead, the brain edits reality gently, smoothing the gaps. You live not in the present instant, but in a softened stream that makes sense of chaos. This editing creates odd effects. Threats appear closer than they really are, because long ago it was better to flinch too soon than too late. A shadow rushing past the corner of your eye might only be a branch, but your mind reacts as though danger has brushed your shoulder. The same trick colours our sense of time. Waiting for a kettle to boil can feel eternal, every second stretched thin. Yet 5 minutes of laughter with a friend can vanish in a blink. Time seems to thicken or thin depending on how the brain filters experience. Boredom drags, joy rushes. Fear compresses each detail so tightly that later you remember it as though it unfolded in slow motion. Even the colours of the world are illusions woven for comfort. At sunset, when the sky blazes orange and crimson, you feel those hues belong to the heavens themselves. But the truth is simpler and stranger. Molecules in the atmosphere scatter blue light, leaving behind reds and golds. The sky is not painted orange. It is your brain interpreting scattered light and calling it beauty. If illusions shape something as near as a shadow or as common as a sunset, imagine what they do to our view of the sun itself. To our eyes from the ground, the sun seems golden, sometimes gentle, sometimes blinding, sometimes slipping to the sea with a crimson glow. But climb above the atmosphere, past the air that scatters and softens, and the sun is dazzling white. It is not red or gold. In truth, it pours photons most strongly in green, though we never see it as green. To us it appears as a blend, a steady white fire. We call it yellow, orange, even red. But these are stories made by air and perception, and what we see is not even the full flood. Alongside the visible light are rivers of radiation our eyes cannot know. Ultraviolet rays stream into the skin, unseen yet felt. Infrared warmth spills across your hands when you lift them to the light, though no red glow accompanies it. Radio waves sweep outward, invisible, unstoppable, caught only by the machines we build. The sun, steady in the sky, is more than the colours we perceive. It is a chorus of light, much of it silent to our senses. Our brains are marvellous, but narrow. They filter, they soften, they miss far more than they capture. That is why humans build extensions to sight. Lenses, mirrors, detectors, telescopes. We stretch vision into wavelengths our eyes ignore. We shrink worlds into view through microscopes, and we enlarge distant galaxies until their light fills our screens. And yet, even with all this borrowed perception, some truths remain hidden. Photons, for all their brilliance, cannot show us everything. They are trapped within the sun for thousands, sometimes millions of years, bouncing from atom to atom before escaping. A beam of sunlight that warms your face this morning, may have begun its journey long before our ancestors spoke of fire. Light is fast, but in dense matter it is delayed. Neutrinos are different. Born in the same nuclear furnaces, they slip away in seconds. They pass through matter as if it were almost empty, carrying with them a real-time whisper of the sun's heart. If you could see neutrinos, you would not be looking at light delayed by millennia, but at the fusion itself as it happens now. Your eyes cannot, of course, and neither can mine, but that is why the story of neutrinos matters. They are the messengers of places photons cannot reach, from the sun's hidden core to the first second of the universe itself. So as you rest tonight, think of how your vision is already softened, filtered, stretched by the brain into something easier to bear. Reality is always one step removed, edited kindly before it reaches you. And just as your senses can deceive you, the universe hides its own truths. To discover them, we will need to follow the trail of neutrinos, the ghostly particles that slip through you even now, uncountable, untouchable, yet essential to understanding where we came from. In the next session, we will turn fully to the sun itself and see how its true colours and invisible floods prepare the stage for the ghosts that reveal its secret heart. When you think of the sun, it is tempting to picture it as a great golden coin pressed against the sky, a circle that warms the earth and sets the rhythm of our days. For as long as humans have lifted their faces to its light, we have spoken of it in the language of gold, amber, flame and fire, in paintings, in myths, in the quiet memory of childhood afternoons. The sun is rarely anything but yellow or orange. Yet this picture, vivid though it is not quite true. The colours we assign to the sun are less about the star itself and more about the veil through which we view it, a veil woven by the air around our planet and the habits of our own eyes. If you were to rise high above the atmosphere, to climb beyond the reach of scattering molecules and dust, the sun would not be golden at all. It would blaze white, a searing brightness that holds every colour within it. The whiteness of the sun is not emptiness, but fullness. It is the blending of countless photons of different energies into a single dazzling flood. It shines most strongly in the green portion of the spectrum, though the star does not appear green to us. Our eyes and brains, working together as translators, combine the wavelengths into what feels to us like neutral daylight, a whiteness that holds no single shade yet contains them all. From the ground, however, the story changes. The air scatters blue light more than red, which is why the sky by day is painted blue while the sun seems to drift into warmer tones. At sunrise and sunset, the light travels through more atmosphere, scattering away most of the short wavelength blues, leaving only the reds and oranges to slip through. It is this filtering that turns dawn and dusk into the fiery spectacles we love, though the sun itself has not changed its song. The instrument is steady, but the hall through which the music passes colours the notes. This scattering not only paints the horizon, it also shapes our emotions. A golden morning may feel warm and promising, while a red sunset can stir nostalgia or calm. Yet both are illusions created by the air. The sun above the veil is impartial, its colour steady, its brightness unflinching. It is our vantage point, our filter of molecules and dust that makes it seem so variable. The beauty is no less real for being an illusion, but it is worth remembering that illusions are all around us, shaping what we think of as truth. And if the visible colours are already filtered, they are also incomplete. The sun pours far more than what we can see. Alongside the rainbow of visible light come waves invisible to our eyes. Ultraviolet radiation floods the earth constantly, unseen yet powerful, capable of both sparking the production of vitamin D in our skin and burning it if we linger too long. Infrared waves spill warmth, wrapping us in heat that has no colour but can be felt with closed eyes. And beyond even these are streams of radio waves, silent, passing through walls and clouds, ignored by our retinas. but caught easily by antennas. Imagine standing outside on a bright day and holding your hand to the sunlight. You see pale skin lit by white glow, but in truth your hand is being touched by more than light. Invisible rays slip through and around, some warming, some nudging chemical reactions in cells, some carrying energies that no human sense has ever directly perceived. Our bodies know only a sliver of the spectrum, and even that sliver is altered by the atmosphere and the brain. To think of the sun as yellow or orange is like listening to a symphony through a closed door and assuming that only the muffled notes you hear are the whole performance. To reach further, we build instruments that can detect the unseen. Telescopes tuned to infrared reveal cool, dusty regions where stars are born, glowing faintly in shades no human eye could ever see. Ultraviolet detectors capture the fierce brilliance of young stars and the hot, active surfaces of galaxies. Radio telescopes map vast jets and arcs that stretch across interstellar space, structures invisible to sight but undeniable when traced through longer waves. Each tool adds another piece to the puzzle, another layer of perception layered onto our narrow vision. And yet, even with all these borrowed senses, there remain truths that ordinary light cannot reveal. Deep within the sun's core, where hydrogen fuses into helium, photons are born in blinding numbers. But the star's dense plasma traps them. Each photon collides, scatters, is absorbed and re-emitted over and over. Their journey outward is not a straight line, but a staggering maze, a random walk that can last thousands, even millions of years. The light that warms your skin today may have been created when early humans still painted on cave walls, or even earlier. The sun's visible face is not the present tense of its core, but a memory delayed by unimaginable journeys. This is why another messenger is needed, a quieter one, a ghost. Neutrinos are created in the same nuclear reactions that generate photons, but they do not linger. They slip free of the sun in seconds, passing through its matter almost untouched, racing outward and through space, through Earth, through you, without pause. Unlike photons, they do not tell us what the sun was like in the distant past. They tell us what it is doing now, in the instant of your listening. The sun's colours, then, are both real and illusory. They are real in the sense that they are the light that meets our eyes, scattered, filtered, softened. But they are illusory in that they are not the sun's truth. The star itself does not change from yellow to red to white. It is steady, impartial, radiant. We see it through veils, and those veils shift with time of day and angle of view. Beyond those veils, hidden in streams of invisible radiation and in torrents of neutrinos, lie stories that no ordinary eye can catch. As you sit with this thought tonight, consider how narrow our slice of reality is. We are built to see one thin band of colours, to call the sun golden or crimson when it is neither. We are creatures of illusions, and yet within those illusions we find beauty, meaning, comfort. The trick of perception is not a flaw, but a kindness. Still, if we wish to know more, if we wish to catch the whispers of the universe's first seconds, we must look beyond what our eyes alone can tell us. In the next session, we will step from these veils of colour into the ways humans have learned to extend vision itself, to borrow new senses, and to begin the chase for the ghosts that slip through light and matter alike. When you close your eyes, the world does not vanish. You still hear the hum of a fan, the distant murmur of a car passing, perhaps the faint creak of wood settling in the walls. Human senses are varied, but they are also limited. Our eyes can take in only a sliver of the electromagnetic spectrum. Our ears only a small band of vibrations. Our skin notices only certain temperatures before calling them pain. Our tongues distinguish a handful of flavours. For all the richness of the world, our bodies give us only a tiny window into it. And yet, despite this narrowness, we have always been restless. We have always reached for more. The principle that guides this reaching is simple. though it does not feel simple when you first hear it. To see something small, you need to use waves that are shorter than the object you wish to study. Imagine trying to trace a fine detail with a thick marker. No matter how careful you are, the lines will blur together. Only a sharp pencil with a tip smaller than the detail will do. Light works the same way. Visible light has wavelengths on the order of hundreds of nanometers. That is fine for seeing a tree, or the lines on your palm, but it is far too coarse to reveal the delicate threads of a virus or the shape of an atom. To reach those scales, we needed to borrow different messengers, electrons with far shorter effective wavelengths in microscopes, X-rays that slip between atoms, neutrons that scatter like subtle probes. Each time the rule is the same. Finer details require finer tools. Telescopes follow the same principle, though in the other direction. To see distant galaxies or clouds of cold gas, we must turn to wavelengths that can slip through dust. Wavelengths our eyes were never built to catch. Radio telescopes sprout enormous dishes to listen to waves meters long, signals that pass quietly through clouds that would block visible light. Infrared instruments peer into nurseries where stars are forming, their warm glow hidden behind curtains of dust. Ultraviolet detectors catch the fierce brilliance of stars so hot they can hardly be imagined. In each case, humans have taken the sliver of perception nature gave us and stretched it outward, upward, downward, into ranges once invisible. It is easy to forget how recent this expansion has been. For almost all of humans' history, the night sky was studied only with the naked eye. Patterns of stars were mapped, their risings and settings used to guide planting, sailing and ritual. The telescope in the early 17th century was a revolution not just in technology, but in perception. Suddenly the moon revealed craters, Jupiter showed moons of its own, Saturn displayed rings. Galileo once wrote that the Milky Way, which looked like a smear of milk to the naked eye, resolved into countless stars when seen through a telescope. It was as though an entire hidden city had been discovered behind a curtain. That curtain has continued to lift, one wavelength at a time. The 20th century added radio astronomy, X-ray astronomy, infrared detectors, orbiting telescopes freed from the blur of Earth's air. Each step was a reminder that what we thought was empty was full. What we thought was silent was singing. Every new tool was another borrowed sense, another way of listening to a universe too large and too subtle for us alone. And yet, even with all these borrowed senses, there are still limits. The most striking example is the sun itself. Light cannot reveal its heart in real time, only a delayed echo thousands of years old. The colours we see are scattered, the radiation we detect only partial. If we want to know what is happening at this very moment, in the very core, we need a messenger that does not stumble, that does not scatter. We need particles that treat matter almost as though it is not there. We need neutrinos. Neutrinos are unlike light in nearly every respect. They have no charge, no colour, no taste to our senses. They do not spark against your retina, do not warm your skin, do not leave a trace of sound in the ear. They move through walls, through the earth, through oceans without pause. If light is like a letter in the post, delayed, shuffled, sometimes lost along the way, neutrinos are like whispers that travel instantly, slipping through every obstacle. But to hear them, to notice them at all, we must borrow new senses stranger than any telescope or microscope we have ever built. This is the pattern of human exploration, a recognition of limits followed by invention. When our eyes prove too coarse, we learn to focus glass and metal into telescopes and microscopes. When visible light faltered, we learn to listen to radio waves, to photograph the world in X-rays, to paint images with infrared glow. Each expansion was at first met with surprise, then with wonder, and finally with familiarity. Perhaps neutrinos will follow the same path. For now they remain at the threshold, faint, elusive, ghostly. but they may yet become another borrowed sense, another way of perceiving the universe, showing us what light never can. As you drift towards sleep, imagine yourself as a creature carrying only a narrow window of sight, yet surrounded by instruments that extend those senses outward like wings. Each one adds a new colour to the unseen rainbow, a new tone to the silent symphony, and among them, waiting, are the neutrinos, the most unlikely messengers of all. In the next session, we will rise above the clouds themselves, into the thin air where one of our great borrowed eyes once flew, a telescope carried high aboard an airplane, chasing the hidden warmth of stars through the infrared sky. There is something quietly magical about flying. You take a seat, feel the hum of engines, and soon the world below slips away. A patchwork of fields and rivers slowly hidden by blankets of cloud. Looking down from the window, the earth feels smaller, and the sky feels impossibly wide. Yet for astronomers, the true gift of flying is not the view down toward the earth, but the view upward through clearer air toward the hidden universe. For light, even more than for people, the atmosphere is both a protector and a barrier. It shields us from rays that would be dangerous, but it also blocks vast regions of the spectrum, making Earth's surface a dim vantage point compared to what lies just above. This is why scientists once placed a telescope on an airplane and sent it soaring above most of the atmosphere. It was called SO5A, the Stratospheric Observatory for Infrared Astronomy. Imagine a Boeing 747, the kind that normally carries travellers and luggage, carefully modified to hold a telescope with a mirror over 2.5 metres wide. Night after night, Sophia would climb above 99% of Earth's water vapour, because water vapour is what blocks most infrared light. From that lofty perch, high in the stratosphere, the telescope could finally glimpse the warm glow of things that had remained invisible from the ground. Newborn stars swaddled in dust, dying stars releasing their final breaths, the soft outlines of planetary systems forming from gas and debris. Infrared light is warmth, a longer wavelength cousin of the visible colours. You know it in the way a stove radiates heat, even when the coils are no longer glowing, or in the way your skin warms when you stand near a campfire though no flame touches you. The universe is filled with such warmth. Clouds of dust and gas that are opaque to visible light shine gently in infrared. Entire galactic cores, thick with obscuring matter, blaze in these wavelengths. Sophia was an eye trained not on the ordinary glow of stars, but on the hushed warmth of what lies behind them. Flying through the stratosphere at night, the observatory became something more than a machine. To those who worked on it, it was like borrowing the eyes of a mythical creature, able to peer through veils that blinded ordinary sight. Pilots guided the aircraft into stable paths, engineers monitored instruments, and astronomers, bundled against the chill of high altitude, watched as the telescope gathered light that had travelled for millions of years only to be swallowed by the Earth's lower air. Up here, at last, those photons met a mirror, bounced into sensors, and were transformed into data. Delicate signals that told of stars in their infancy, planets coalescing from disks, galaxies thick with dust. It is worth pausing to imagine one of those nights. The airplane hums steadily, a sound like the inside of a seashell. The windows are darkened, the cabin lit only by the glow of screens. Outside, far below, clouds drift, silent and immense. And in the belly of the aircraft a mirror swivels, catching faint warmth from faraway objects. Warmth that carries the memory of events unimaginably distant in both time and space. You might picture an astronomer leaning close to a monitor, watching the faint trace of a star's birth appear as a curve on a screen. The cosmic equivalent of hearing a baby's first heartbeat. What Sophia taught us is that perception can be borrowed in ways both creative and unexpected. You do not need to build a mountaintop observatory, nor a satellite beyond Earth's grasp, if you can simply rise above the veil that blinds you. A plane is not the most likely home for a telescope, and yet it worked. For years, Sophia opened a window into the universe's hidden warmth. It showed us that cosmic birth and death are not events of blazing fireworks alone, but also of quiet, dusty processes visible only in soft infrared glow. Eventually, Sophia retired, its wings folded back into history. But its legacy is a reminder that our senses are not fixed. They can be extended in ways that would have astonished earlier generations. To see the unseen, you do not always need to change your eyes. You need only to change your vantage point. And yet, even Sophia had its limits. It could catch photons of certain kinds, photons that had slipped through dust or been stretched by distance, but it was still dependent on light. And light, for all its reach, cannot tell every story. As we have already seen, photons can be delayed, scattered, hidden, lost in dense matter. They can only reveal the universe as far back as the moment when space itself became transparent, some 300 or 80,000 years after the beginning. For anything earlier, for the very first second, light offers nothing but silence. That is where neutrinos enter. They are not photons. They do not scatter in the same way. They are not absorbed by dust, nor delayed by dense matter. They travel almost untouched, indifferent to obstacles. If we could build an eye for neutrinos, it would be like a telescope that sees through every wall, every veil, every curtain the cosmos has ever drawn. It would not show us only the surface of stars or galaxies in their late bloom, but the very first instant after the universe began. For now, such an eye is only a dream. But humans are stubborn dreamers. We have placed mirrors in deserts, dishes on mountain tops, telescopes in orbit, even observatories on the wings of airplanes. Again and again, we have found ways to extend our vision just a little further, to borrow another sense from the world around us. It is only natural that our reach now extends toward the neutrino, the most ghostly messenger of all. So as you settle deeper into rest, imagine yourself seated on that airplane, high above the clouds, the night vast outside, the stars brighter than they ever appear from the ground. Picture a telescope quietly turning, catching whispers of warmth that no eye could ever see, and think of how much more remains, waiting beyond light itself, carried not by photons but by particles that pass through you even now without a sound. In the next session, we will return to the story of their invention, to the moment when a troubled physicist proposed them as a desperate solution, not knowing he had named the ghosts that would one day help us glimpse the universe's very first breath. For all its brilliance, light is not always the most faithful messenger. We're accustomed to thinking of photons as the ultimate carriers of truth. They cross the void of space, deliver the colours of stars to our eyes, and bring us news from galaxies so distant that their light has been travelling since long before humans walked the Earth. It is tempting to believe that if we only had better telescopes, larger mirrors and clearer skies, then light could tell us everything. Yet there are times when light falters, when it is trapped, delayed or scattered, until the story it carries is blurred beyond recognition. Consider the sun, the great star that sustains us. Every photon of sunlight that touches your face began its journey in the sun's core, in the fusion of hydrogen into helium. But those photons do not stream outward like arrows shot from a bow. The sun is so dense inside that photons scatter endlessly, colliding with electrons and protons, being absorbed and re-emitted, wandering in a drunken zigzag through plasma. Scientists sometimes call this a random walk, a phrase that suggests both the chaos and the patience of the process. A single photon might take thousands, even millions of years to reach the surface, stumbling forward a few millimeters before scattering again, like a traveller lost in a fog too thick to navigate. By the time that photon escapes into space and races across 150 million kilometers to Earth, the story it tells is hopelessly out of date. The light warming your skin this morning could have been born before humans invented writing, or before glaciers retreated from the last ice age. The sun you see is not the sun as it is now, but the sun as it was long ago. For studying the present tense of the sun's heart, light is simply too late. This delay is not unique to our star. It is written into the universe itself. When the cosmos was less than 400,000 years old, it was so hot and dense that light could not travel freely. Photons were constantly scattered by the charged soup of protons and electrons, locked in an endless cycle of collisions. Only when the universe cooled enough for atoms to form did space become transparent. The glow from that moment, stretched by billions of years of expansion, is what we now see as the cosmic microwave background. It is a magnificent map, but it is also a reminder of a limit. Light can show us the universe as it was 380,000 years after the beginning, but no earlier. The first second, when everything that would become galaxies, stars and planets was still in a seething state of density and heat, remains hidden. Photons cannot pierce that curtain. Even in more ordinary cases, light often fails to reach us intact. Dust clouds obscure the birthplaces of stars, swallowing visible light and leaving only faint traces behind. The crowded cores of galaxies are shrouded in matter that hides their secrets from optical eyes. Whole events, like the collapse of stellar cores, unfold behind walls of plasma that photons cannot cross in time. We have grown used to believing that seeing is knowing, but in truth sight alone is only partial. It is in these silences that scientists have learned to long for another kind of messenger, one not so easily delayed or silenced. If photons are like travellers who are easily distracted, stopping at every tavern along the way, what would it mean to have a traveller who moves straight through, ignoring every obstacle, never lingering, never scattering? What would it mean to have a signal that tells us what is happening now, not what happened long ago? Nature has provided such a messenger, though it is almost too shy for us to notice. Born in the same nuclear reactions that create photons, these particles slip away instantly. They pass through the sun's matter in seconds, racing outward unimpeded, carrying with them the true present tense of the star's core. They were also there in the first second of the universe, flying free while photons were still imprisoned in plasma. If only we could listen to them, we would hear stories that light has never been able to tell. Of course, these particles are not easy companions. They do not glow. They do not warm your skin. They do not paint the sky in colours. They are ghosts gliding through matter almost without a trace. Every second, billions of them pass through your body without you ever noticing. They slip through mountains and oceans as if they were shadows. To catch them requires patience, cleverness and detectors so immense and delicate that they are more like instruments of listening than instruments of vision. At first, these ghost particles were only imagined, born out of necessity rather than observation. Physicists struggling with puzzling results in their experiments began to suspect that something unseen was escaping detection. It was not that they wanted to invent a new particle. They were almost embarrassed to do so. But the numbers would not balance without it. Conservation of energy, that most sacred law of physics, seemed to demand an invisible partner, a hidden participant in the play of matter. It is strange to think that one of the most important discoveries in modern physics began not with triumph, but with discomfort, not with clarity, but with confusion. The light was not enough, the equations did not agree, and the only solution seemed to be a ghost. In the next session, we will meet the man who first dared to suggest it, a reluctant genius who began his letter to colleagues with an apology, introducing a particle so elusive it seemed almost like a joke. And yet, this hesitant proposal would open the door to an entirely new way of seeing the universe. There is a certain kind of silence in science, the kind that comes not from the absence of data, but from the discomfort of results that refuse to make sense. By the late 1920s, physicists had grown confident in their ability to describe the invisible. The electron had been measured, the proton was well established, and the photon had become a familiar companion. Atoms seemed no longer mysterious fogs but orderly systems with rules, and yet, tucked inside the study of radioactive decay, there was a problem that would not go away. In beta decay, an unstable nucleus releases an electron. It seems straightforward enough, another kind of radioactive process alongside alpha and gamma decays. But when experimenters measured the energies of the electrons flying out, they found something unsettling. The electrons did not all have the same energy, as one might expect if they shared it with a single partner in the decay. Instead, they emerged with a wide range of energies, some high, some low, spread out as though something invisible was stealing or sharing the energy in unpredictable amounts. This result was more than an oddity. It challenged the sacred principle of conservation of energy, the idea that energy is never created or destroyed but only changes form. For generations, this principle had been the heartbeat of physics, as reliable as the rising sun. If electrons were emerging with missing or excess energy, then either the principle itself was wrong, or something else, unseen, was carrying away the balance. Many physicists hesitated. To suggest that conservation of energy might fail inside the atom felt like heresy, but to propose a new, invisible particle was almost as outrageous. The laboratories echoed with quiet frustration. Measurements were checked, theories recalculated, but the puzzle persisted. It was in this climate of unease that Wolfgang Pauli, an Austrian physicist known for his sharp intellect and sharper criticisms, sat down to write a letter. The year was 1930, and Pauli was attending a gathering in Tübingen. He was not even present at the meeting where his letter was read aloud. He had sent it in his place, as though unwilling to fully own the audacity of its contents. He began with an apology, writing, "Dear radioactive ladies and gentlemen," and confessing that he was proposing something he himself found troubling. His solution to the beta decay puzzle was to imagine a new particle, one that carried away the missing energy but was so elusive that no one had ever seen it. It would be electrically neutral, almost massless, and nearly impossible to detect. He called it, at first, a neutron, not yet knowing that another particle with that name would soon be discovered by James Chadwick. Later, Enrico Fermi would rename Pauli's ghost the neutrino, the little neutral one, a word that carried both a hint of humility and a recognition of its strangeness. Pauli did not propose his particle with triumph. He called it a desperate remedy, a last resort to preserve the cherished law of energy conservation. It was a whisper of a particle, invented not because he wanted it to exist, but because the universe seemed to demand something like it. His colleagues received the letter with a mix of amusement and skepticism. Some thought it clever, others thought it fanciful, and almost everyone thought it might never be confirmed. How do you prove the existence of something that slips through matter without leaving a trace? And yet, the beauty of science is that even ghosts, if they are real, must eventually leave footprints. If Pauli's particle was true, then it must sometimes collide, however rarely, with the atoms it passed through. The task was monumental, like waiting for a single snowflake to land in your hand during a storm without ever looking up. But impossibility has a way of inspiring the patient, and so, slowly, the hunt began. For Pauli himself, the neutrino became both a point of pride and a source of unease. He had given physics a solution, but it was one that hovered on the edge of belief. In later years, he would joke about it, saying he had invented a particle that could never be detected, a convenient ghost to tidy the equations. And yet, history would prove him right. Looking back now, it feels almost poetic that the neutrino entered the world not with a bold proclamation, but with an apology. Pauli did not stand at a podium to announce a new building block of nature. He wrote a hesitant letter, admitting that he might be suggesting something absurd. The ghost particle was born in humility, as though it demanded a quiet entrance to match its quiet passage through the universe. The story of the neutrino reminds us that science is not only about discovery but about discomfort. Progress often begins when something fails to add up, when the familiar breaks down, when cherished principles seem at risk. The neutrino was not invented to dazzle, but to repair. It was the patch on a tear in the fabric of physics, a patch that turned out to be real. As you drift deeper into the calm of this night, imagine the scene. A physicist at his desk, scratching out words by lamplight, sighing as he proposes an invisible companion no one has ever seen. Around him the world goes on, unaware that a new chapter in physics is being written. The particle he reluctantly imagines will one day allow us to peer into the hearts of stars and into the first second of time itself. But in that moment it is only an idea, fragile, hesitant, uncertain. In the next session, we will follow that ghost particle from theory into reality, to the experiments of the mid-20th century where patient scientists finally managed to capture its faint signature. We will stand with them in quiet laboratories, watching for the tiniest flickers of light that confirmed Pauli's apology was not a mistake, but a revelation. For more than 20 years after Wolfgang Pauli's hesitant letter, the neutrino remained a ghost in theory, a patch on physics that many accepted but few truly believed in. Scientists spoke of it in their equations and lectures, but in laboratories it remained absent, a phantom whose existence was taken on faith. Even Pauli himself, though brilliant and bold in other aspects of his work, wondered aloud whether it would ever be found. To many, it seemed destined to remain a mathematical fiction, a polite way of saying something unknown leaves with the energy, and leaving it at that. But the mid-20th century was a time when patience and technology began to catch up with imagination. New reactors were humming, releasing streams of radiation that had never existed before in such concentrated form. These reactors were more than machines for power. They were also fountains of particles, cosmic laboratories built by human hands. Among those who saw in them a unique opportunity were two American physicists, Clyde Cowan and Frederick Raines. Raines, in particular, was known for his daring approach to problems. He believed that the neutrino could, with enough ingenuity, be coaxed into revealing itself. He once described the challenge in a way that showed both humour and determination. It was like trying to hear the footsteps of a single cat in the middle of a thunderstorm. Almost impossible, yes, but not absolutely impossible. And in physics, not absolutely impossible is often enough to inspire someone to try. The plan he and Cowan devised was bold. If neutrinos interacted only through the weak force, then the odds of catching one were tiny, but not zero. The trick was to create conditions where billions upon billions of neutrinos passed through a detector every second, increasing the chance that just a few would collide. Nuclear reactors splitting atoms at furious rates produced exactly that. Floods of anti-neutrinos pouring invisibly out of their cores. All that was needed was a patient ear to listen for them. The detector they built was both massive and delicate. They filled tanks with hundreds of litres of liquid scintillator, a material that would release faint flashes of light when struck by energetic particles. Around the tanks they placed instruments to catch even the smallest glimmers, the faintest spark in the dark. When an antineutrino happened to collide with a proton in the liquid, the reaction would produce a positron and a neutron. The positron would almost instantly meet an electron, the two annihilating in a burst of light, while the neutron would linger just a little longer before being captured, releasing second flash. Two signals, separated by a small delay, would be the unmistakable fingerprint of a neutrino event. It must have been a strange vigil, sitting in the laboratory, surrounded by tanks of liquid and instruments, waiting for flickers that would almost never come. Most of the time, the detectors recorded nothing unusual, only the background hum of the universe. The ghost streamed through the tanks endlessly, untouched and untouchable. But then, very rarely, one would brush against a proton and leave its twin flashes. At first, the signals were so rare and faint that skepticism remained. Was it truly the neutrino at last, or just noise, coincidence, some unseen source of error. Cowan and Rayner's refined their setup, tested against every background they could imagine, and slowly the pattern emerged with undeniable clarity. The two-step flash, the annihilation, and the capture, repeated often enough to rise above the noise. Against all odds, they had heard the footsteps of the ghost. In 1956 they announced their result. The neutrino had been detected. Pauli's desperate particle, born in apology, was no longer only a placeholder in theory. It was real, measurable, and part of the family of nature's building blocks. For the first time, humankind had reached into the invisible flood of neutrinos and pulled out proof. The discovery was quiet, almost subdued compared to other great announcements. There was no glowing photograph, no streak of tracks in a cloud chamber to show the public, only graphs, data, statistics, the subtle language of rare events. But to physicists it was a triumph. It confirmed that conservation of energy truly held, even inside the atom. It vindicated Pauli's courage in proposing the unseeable, and it opened the door to a new era in particle physics, one in which the ghostly neutrino would take its place as a key actor in the cosmic story. Raines would later receive the Nobel Prize for this achievement, though Cowan, who had passed away earlier, did not live to see the honour. Their names, however, are forever linked to that first capture, that first whisper of the neutrino's presence. What is perhaps most striking about the story is how subtle the proof was. To detect the neutrino, they did not need a colossal accelerator smashing particles together in violent flashes. They needed patience, stillness, and the willingness to trust faint signs. It was less like hunting a beast, and more like listening for the flutter of wings in the night. Science is often imagined as bold and noisy, but here it was quiet, patient, gentle. As you drift further into rest, think of those tanks filled with silent liquid, standing vigil as the ghosts of the universe streamed through them by the trillions. Almost all passed unnoticed, but every once in a while one left behind a flicker of light, like a ghost agreeing to a handshake. The neutrino at last was real. In the next session, we will follow those ghosts upward, out of reactors and into the sun itself, where they pour in unimaginable numbers. We will listen to the experiments that sought to catch them in the depths of a mine, and the great puzzle that emerged when most of them seemed to have vanished along the way. When Clyde Cowan and Frederick Raines finally caught their elusive neutrino in 1956, they had proven the ghost was real, but in a sense they had only opened the door. The reactor experiment showed that neutrinos existed and could be detected, but it was like hearing a whisper from a single voice in a crowded hall. What physicists truly wanted was to listen to the great choir of neutrinos streaming constantly from the sun. If neutrinos were born in the nuclear reactions that powered stars, then studying them directly would be like listening to the sun's beating heart, hearing its core in the present moment rather than through photons that were thousands of years out of date. It was this ambition that drew Raymond Davis Jr., a quiet, methodical chemist, into one of the strangest and most patient experiments ever attempted. His idea was simple in concept but enormous in scale. Build a detector large enough that even the most elusive neutrinos would occasionally leave a trace, and bury it deep enough underground that no other kind of particle could confuse the signal. The detector he envisioned would not look like a telescope or a microscope. It would not resemble any ordinary scientific instrument at all. Instead, it would be a vast tank filled with an unlikely liquid, perchloroethylene, the same chemical used in dry cleaning. The location was the Home State Gold Mine in South Dakota, nearly a mile underground. By building his experiment so deep beneath the surface, Davis could shield it from cosmic rays and other background radiation. Almost nothing could penetrate so far but neutrinos which slipped through rock as though it was smoke. There, in the cool silence of the mine, he installed a tank holding 600 tons of cleaning fluid, a volume so great that it resembled more an industrial reservoir than a laboratory instrument. The idea was that when a neutrino from the Sun collided with a chlorine atom in the liquid, the atom could be transformed into argon. Argon, being a noble gas, would not bind to the liquid. It would simply wait, like a faint exhalation, until Davis and his team came to collect it. Every few weeks, the experimenters would flush the tank, drawing out any atoms of argon that had formed. The numbers were tiny, often only a handful of atoms in the entire vast sea of liquid. Imagine standing before an ocean and searching for a few grains of sand that had been dropped in while you were away, and you will have some sense of the delicacy involved. Yet Davis persisted, patiently gathering his samples, carefully counting the few argon atoms that marked the passage of solar neutrinos. What he expected, according to the best models of the Sun, was a steady rate of neutrino interactions, a clear signal corresponding to the immense flood of neutrinos pouring from the solar core. What he found, however, was something altogether stranger. Instead of the predicted number, his experiment revealed only about a third. 2/3 of the expected neutrinos were missing. At first, the discrepancy seemed almost too large to believe. Perhaps the calculations of the Sun's interior were wrong. Perhaps the tank was not working as designed. Perhaps the argon was escaping in ways no one had considered. But Davis was meticulous. His procedures were checked again and again, and the results held. The missing neutrinos were not a fluke of chemistry or engineering. They were real. Thus was born what became known as the solar neutrino problem, a mystery that would haunt physics for decades. If the Sun was producing fewer neutrinos than theory predicted, then perhaps the models of stellar fusion were incomplete. But the models had been tested in countless other ways and seemed robust. If, on the other hand, the Sun was working as expected, then something must be happening to the neutrinos themselves on their journey to Earth. Either way, the result was unsettling. Other detectors were built in time, each with different methods, in different parts of the world. Some used water, waiting for faint flashes of light from neutrino collisions. Others used gallium instead of chlorine. Each experiment, designed to avoid the flaws of the others, returned results that agreed with Davis's. The neutrinos from the Sun were consistently fewer than predicted. It was not just his mine, not just his tank, not just his chemistry. Something profound was happening in the universe's smallest messengers. For years, the scientific community wrestled with the puzzle. Some argued that the Sun's interior was cooler than expected. Others speculated that unknown processes might be altering the nuclear reactions themselves, but these explanations required rewriting much of what was otherwise consistent about solar physics. Increasingly, suspicion turned back to the neutrino. Perhaps the ghost was not so simple after all. Perhaps as it crossed the gulf of space it changed. Through it all, Davis continued his work in quiet persistence. He was not a man given to dramatics. Year after year he flushed the tank, counted the argon atoms and reported the same baffling shortfall. His experiment ran for decades, becoming one of the longest and most patient in scientific history. By the time he was recognised with a share of the Nobel Prize in 2002, he had become a symbol of endurance in science, a man who listened to the Sun's whispers faithfully for 30 years, even when most of those whispers were missing. There is something soothing in the image, deep, underground, in the silence of an abandoned gold mine, a tank of cleaning fluid quietly waiting for ghostly particles from the Sun. Above, the world went on with its noise and haste, but below, in the shadows, patience ruled. The neutrinos streamed in unimaginable numbers through rock and air, through mountains and oceans, through Davis himself as he worked, and only occasionally would one leave its subtle mark. As you lie here now, billions of solar neutrinos are passing through you each second, unnoticed, untouchable, but real. Some of them are the same kind that Davis sought, the ones that were expected but so often missing. To think of them is to feel a kind of connection with the invisible, a reminder that much of reality flows through us silently, indifferent to our senses. In the next session, we will see how the mystery of the missing neutrinos was finally solved, not by adjusting the sun's physics, but by realising that neutrinos themselves are shapeshifters, changing identity as they travel, like dancers trading masks mid-performance. For decades, the solar neutrino problem lingered like a stubborn riddle. Ray Davis's underground tank continued to whisper the same result. The sun's neutrinos were arriving, but in numbers far smaller than expected. Other experiments joined his vigil, built with different techniques and different materials, yet they too reported the same shortfall. No matter how the detectors were designed, the missing neutrinos refused to appear. To some, this seemed to suggest that the models of the sun itself must be wrong, that its nuclear furnace was burning in some unfamiliar way. But the sun's brilliance, its energy, its stability, and the agreement of theory with so many other observations made that explanation increasingly unlikely. The mystery had the feeling of a magician's trick. The neutrinos were produced, they were sent, and yet somewhere between the sun and Earth 2/3 of them vanished. The answer, when it came, was stranger and more beautiful than almost anyone had imagined. The neutrinos had not vanished at all. They had only changed their identities. Neutrinos, it turns out, are not born into a single, unchanging form. They come in 3 flavours, tied to the 3 types of charged particles they sometimes accompany: the electron neutrino, the muon neutrino, and the tau neutrino. The sun's fusion reactions produce primarily electron neutrinos, and so Davis's detector in South Dakota was designed to capture those alone. But the neutrinos themselves had other ideas. As they travelled the 93 million miles from the sun to Earth, many of them quietly shifted flavour, turning into muon or tau neutrinos, identities to which Davis's chlorine atoms were blind. The process is called oscillation, and it is one of the most hauntingly poetic phenomena in physics. Imagine 3 dancers on a stage, each wearing a different mask. One begins in front, easy to see, but as the performance goes on, they trade masks, stepping in and out of view. You think you're watching one dancer all along, but when the masks are lifted, you realise they have changed places again and again. Neutrinos behave in just this way. An electron neutrino may leave the sun as one identity, but halfway to Earth it may have become a muon neutrino, and by the time it reaches a detector underground it might be tau. At first, this idea seemed almost too strange to accept. Particles had always been considered fixed in their nature. An electron does not suddenly become a proton halfway through its journey. A photon does not decide to masquerade as a neutron, but neutrinos, those ghosts of the cosmos, obeyed subtler rules. They were not pinned to a single form, they were wanderers between identities, slipping from one to another like travellers changing costumes at every border. The proof came slowly, through painstaking experiments around the world. In Japan, the Super Kamiokande detector, a vast cavern filled with 50,000 tons of ultra-pure water, was built to observe flashes of light created by neutrino interactions. In Canada, the Sudbury Neutrino Observatory sank a sphere filled with heavy water 2 kilometres underground in a nickel mine. These instruments were designed not only to catch neutrinos, but to distinguish their different flavours, and what they showed was revolutionary. Electron neutrinos from the sun were indeed fewer than predicted, but the missing ones had not vanished into nothing. They had arrived on Earth wearing new disguises, transformed into muon and tau neutrinos. This discovery solved the solar neutrino problem, and in doing so changed the way we understood the universe. Oscillations could only occur if neutrinos had mass, however small. For decades, the standard model of particle physics had treated them as massless, as weightless shadows that existed only to balance equations. But the dance of oscillations revealed otherwise. To change flavour, neutrinos must carry mass, infinitesimal but real. It was as though the universe had whispered a correction. Even the lightest of ghosts carries weight. The implications were vast. Neutrinos are the most abundant massive particles in the universe, streaming through space in numbers beyond counting. Even with masses trillions of times smaller than that of a grain of sand, their sheer abundance means they shape the cosmos on large scales, influencing the growth of galaxies and the structure of the universe itself. What had begun as a desperate patch to save energy conservation had become a key ingredient in cosmic evolution. And yet, there is something curiously human about the story of oscillations. The missing neutrinos confounded us for decades because we assumed that particles should be rigid, fixed, unchanging. When we finally discovered that neutrinos could slip between identities, it was both shocking and strangely familiar. After all, we ourselves wear different masks in different contexts, shifting roles throughout our lives, appearing one way to family, another way to friends, still another to strangers. Neutrinos, in their ghostly journeys, seem to embody that same restlessness, that refusal to be only one thing. For Ray Davis, the solution came too late to be part of his own work. His detector could never see muon or tau neutrinos, and so for him the mystery remained. But for the generations of scientists who followed, the revelation was transformative. They had finally understood that the sun's voice had not grown faint. It had simply shifted its pitch into registers we had not been listening for. Once new detectors opened their ears to all the voices, the choir of solar neutrinos rang out at full strength, and the problem was resolved. As you drift deeper into stillness tonight, imagine the journey of those neutrinos leaving the sun. They begin as one thing, then quietly change, then change again, until by the time they pass through you, they may be entirely different than when they were born. It is a reminder that even the smallest particles in the universe are not bound to a single identity. They move, they transform, they oscillate, and in doing so they keep the universe honest. In the next session, we will follow this discovery to its deeper implications, exploring what it means for neutrinos to carry mass, why this is a challenge for the standard model, and how their tiny weights ripple outward to touch the very fabric of cosmology. The revelation that neutrinos change their identity as they travel, shifting from electron to muon to tau and back again, was more than a clever solution to the solar neutrino problem. It carried with it a profound implication. For a particle to oscillate between states, it must have mass. This truth is embedded in the mathematics, but it can be understood more simply. Massless particles like photons cannot change in that way. They travel at the speed of a light, forever fixed in their identity. To swap masks, to shift from one form to another, requires the rhythm of time, the beat of a mass that allows them to move more slowly than light itself. The neutrinos' dance of oscillations was therefore a whispered confession. They are not weightless ghosts after all. They carry mass, however tiny. For decades, the standard model of particle physics had treated neutrinos as massless, companions of no weight who existed only to balance the books of nuclear reactions. They were shadows of processes, placeholders in equations, elegant in their absence of burden. The discovery of oscillation shattered that simplicity. To admit neutrino mass was to admit that the standard model, triumphant in so many other respects, was incomplete. It was as though a finely crafted watch, ticking perfectly for decades, had suddenly revealed that one of its smallest gears was not quite what it had seemed. The watch still worked, but it was no longer whole in the way everyone thought. The mass of the neutrino is vanishingly small by ordinary standards. An electron is already one of the lightest known particles, but neutrinos are at least 1,000,000 times lighter still. To weigh one is to weigh a breath against a mountain. Yet the strangeness lies not in their individual frailty, but in their number. Neutrinos are the most abundant massive particles in the cosmos. Every star, every nuclear reaction, every ancient moment of the universe has poured them into existence. And now they drift everywhere. Billions pass through every square centimetre of your skin each second. Multiply that by the vastness of the universe, and suddenly their collective weight is not trivial. Here the sand grain analogy offers comfort. A single grain is almost nothing. It slips between your fingers, lighter than thought, but pile enough of them together and you have beaches, dunes, deserts that stretch to the horizon. Neutrinos are like that. Each is tiny beyond comprehension, a whisper against the roar of heavier particles, but the universe has made so many that together they shape cosmic history. Their combined mass slows the growth of galaxies, influences the clustering of matter, and leaves delicate fingerprints in the cosmic web. To ignore them would be like ignoring the role of sand in shaping shorelines. They are small, but they are many, and in the arithmetic of the cosmos, multitude matters as much as size. For scientists, the realization that neutrinos had mass was both thrilling and unsettling. It meant that physics still held secrets. The Standard Model had been a faithful map for decades, but here was clear evidence that the map was incomplete. Students who once learned that neutrinos were massless now had to be told otherwise, and teachers found themselves explaining that one of the universe's most elusive particles was quietly tugging at the shape of galaxies. In laboratories, new experiments sprang up, aiming to measure exactly how heavy neutrinos are, to pin down the numbers that would tell us how much weight these ghosts truly carry. Yet even now their masses remain among the most uncertain in physics. We know they are not zero, we know they are tiny, we know that their combined weight is less than a fraction of an electron volt, a unit so small it is difficult to imagine. But the precise values remain veiled. The oscillations tell us about the differences between masses, not the absolute numbers. It is as though you are listening to music in a darkened room. You can tell that one note is higher than another, that the intervals between them follow a pattern, but you cannot yet see which instrument is playing or how deep the lowest note truly goes. What makes this discovery so soothing in its strangeness is that it reminds us of proportion. We are used to thinking that what matters most must be heavy, must be grand, must be obvious. Neutrinos defy that expectation. They are proof that what is small, when repeated, enough can tip the balance of entire galaxies. They are gentle lessons in humility, lessons written not in bold strokes but in whispers of mass spread thinly across the universe. If you pause and let the thought settle, you may find it comforting. Every second, billions of neutrinos slip through you. Each carries only the faintest trace of mass, less than a breath, less than a memory. And yet, taken together, they outweigh all the stars that shine. They drift in silence, but their weight bends the story of the cosmos. To rest beneath that knowledge is to feel that even the smallest things have meaning. Even the most elusive ghosts leave an imprint. In the next session, we will turn to one of the puzzles that remains. We know neutrinos have mass, but we do not know the order of those masses. Which is heaviest, which is lightest, and what does the arrangement reveal? It is a question physicists call the mass hierarchy, and it is like listening to an orchestra without knowing which instrument is playing the lowest note. Once physicists accepted that neutrinos must have mass, a new question rose quietly from the equations like music drifting from another room. If they do have mass, then how are those masses arranged? Are they neatly ordered, from lightest to heaviest like the notes of a scale? Or do they follow some stranger pattern, their order inverted, the deepest note not where we expect it? This puzzle, known as the neutrino mass hierarchy, remains one of the most intriguing and unresolved mysteries in modern physics. At first glance, the problem may sound trivial, like asking whether 3 coins in your pocket are stacked in one order or another. But in physics, order matters. The sequence of neutrino masses determines how they influence the evolution of the universe, how they affect the clustering of galaxies, and how they interact with other particles. It also hints at the deeper mechanism that gave them mass in the first place. To learn their order is not only to tidy the shelves of physics, but to glimpse the architecture of the cosmos itself. There are 2 main possibilities. In what is called the normal hierarchy, the electron neutrino is the lightest, with the muon neutrino heavier, and the tau neutrino heavier still. This arrangement feels intuitive, matching the order of their charged partners, where the electron is lighter than the muon and the muon lighter than the tau. In the inverted hierarchy, however, the order is flipped. The electron neutrino's mass lies closer to the top, and the other flavors cluster below it. The intervals between them remain the same, as demanded by oscillation data, but the ladder itself leans in the opposite direction. Experiments so far have not resolved the debate. They have given us the differences between the rungs of the ladder, but not whether the ladder is leaning left or right. It is like listening to an orchestra through a wall. You can hear that one instrument plays higher than another, and you can sense the intervals between notes, but you cannot yet say with confidence which is the lowest, which is the anchor of the harmony. The music is clear, but its foundation is hidden. Physicists have built vast detectors to listen more carefully, hoping to catch subtle effects that reveal the order. Some rely on beams of neutrinos shot through the Earth, comparing how the flavors shift as they travel. Others watch neutrinos from the atmosphere, born in showers of cosmic rays, to see how their oscillations unfold. The patterns are delicate, the differences minute, but within those subtleties lies the answer to the hierarchy. Why does it matter so much? Because the hierarchy is more than a bookkeeping exercise. If the normal ordering is true, then the lightest neutrino is almost massless, and the others build upward from it. If the inverted ordering is true, then two neutrinos share nearly the same mass, and the third is far lighter. Each scenario affects how neutrinos shaped the early universe, how they slowed the growth of structure, and how they fit into theories of unification that try to weave all forces together. The hierarchy may also hold clues about whether neutrinos are their own antiparticles, a deep question tied to the matter-antimatter asymmetry that allows us to exist at all. There is a kind of poetry in the uncertainty. We know neutrinos have mass, we know they oscillate, we know their differences, but we do not yet know their true order. It is as if the universe is playing a symphony and has chosen to keep the lowest note hidden, leaving us to guess at the foundation. We can hear the harmonies, we can measure the intervals, but the baseline remains mysterious. Perhaps it is fitting that the ghosts of physics, so adept at disguise, would keep their weight a secret as well. To a listener drifting towards sleep, this puzzle may seem abstract, but it is worth reflecting on how often mysteries of order shape our lives. A few words rearranged can change the meaning of a sentence. A few notes shifted can alter the mood of a song. A handful of numbers placed in one sequence rather than another can unlock or hide a secret. So it is with neutrinos. Their order is more than an academic detail. It is a key to understanding how the smallest of particles knit into the largest of structures. As you lie still, imagine three musicians standing in a darkened hall, each playing a steady note. You cannot see them, but you hear their sound drifting toward you. You know the notes are different. You can sense the spacing, but you cannot yet say which instrument is the lowest. Perhaps it is the violin, perhaps the cello, perhaps something deeper still. The music is there, but its architecture is veiled. That is the neutrino hierarchy, a harmony without a foundation, a song waiting for its base. In the next session, we will step from order to origin. If neutrinos do have mass, and if their hierarchy remains uncertain, the next natural question is where that mass comes from. Is it born of the same Higgs field that gives weight to other particles, or does it arise from stranger mechanisms, seesaws of hidden partners, secret relatives in the family of matter? To answer that, we will gather at a cosmic reunion where some guests are present, and others may only exist in whispers. Once it was accepted that neutrinos have mass, and once the puzzle of their hierarchy was laid before us like a score missing its baseline, another question arose naturally, almost unavoidably. Where does that mass come from? For the other particles of the standard model, the answer is clear enough. Electrons, quarks, and even the heavy W and Z bosons all gain their mass through the Higgs field, a pervasive energy that fills space like an invisible ocean. Particles moving through that ocean are slowed, given heft, the way a swimmer feels the drag of water. In 2012, the discovery of the Higgs boson confirmed this picture, cementing it as one of the triumphs of modern physics. But neutrinos, it seems, are not content to follow the rules so neatly. Their mass is too peculiar, too tiny, too unlike the others to be explained in the same straightforward way. If the Higgs was solely responsible, neutrinos should be heavier, perhaps not as heavy as protons or neutrons, but certainly not 1,000,000 times lighter than an electron. Something about them suggests another mechanism at work, a hidden source of weight that lies beyond the familiar picture. To imagine it is to imagine a family gathering where almost everyone is accounted for, each relative sitting at the table, chatting loudly, while in the corner a few shadowy figures linger, half seen, barely present, yet essential to the story of the clan. One possibility physicists have proposed is called the seesaw mechanism. Imagine a playground seesaw with a heavy stone on one end and a feather on the other. The stone drags its end to the ground, leaving the feather lifted high but precariously light. In particle physics, the idea is that neutrinos may have heavy cousins, particles so massive that we cannot produce them with any accelerator we have today. Their sheer weight pushes down one side of the seesaw, making the ordinary neutrinos on the other side almost massless. In this picture, the lightness of the neutrino is not an accident, but a consequence of balance. The universe keeps them small by pairing them with partners too heavy for us to ever meet directly. Another possibility is that neutrinos are their own antiparticles, what physicists call Majorana particles. Most matter has an opposite. The electron has the positron, the proton has the antiproton, but a Majorana neutrino would be its own opposite, a strange dual being that blurs the line between matter and antimatter. If this is true, then the universe might occasionally allow two neutrinos to collide and simply vanish, leaving behind nothing but a trace of energy. Detecting such an event would be like catching two ghosts clasping hands and dissolving into air. It would also offer a clue to one of the deepest mysteries of all, why there is something rather than nothing, why matter dominates over antimatter in the cosmos we inhabit. And then there is the suggestion of sterile neutrinos, cousins even more elusive than the ghosts we already know. The three familiar flavours, electron, muon and tau, interact through the weak nuclear force, rare as those interactions may be. But sterile neutrinos, if they exist, would not interact through any force except gravity. They would pass through the universe with even greater indifference, almost entirely hidden, seen only in their gravitational tug on galaxies and cosmic structures. Some believe they could even be a component of dark matter, the invisible scaffolding that holds galaxies together. To imagine them is to picture distant relatives who never attend the reunion, never call, never write, but whose absence is felt in the shape of the family itself. What unites these ideas is not certainty but creativity. The neutrino's mass is so small, so unlike the others, that it demands new thinking. Whether it is a seesaw with heavy partners, or a Majorana identity that merges particle with antiparticle, or a sterile cousin that whispers only through gravity, each scenario stretches the imagination. None is proven. Each is a possibility. But each reminds us that the universe often hides its answers in the faintest places, in the lightest particles, in the ghosts we are barely able to catch. For the scientists who devote their lives to these questions, the pursuit can feel like attending a family gathering where the most important guest has not yet arrived. The chairs are arranged, the conversation's underway, but one seat at the table remains empty. Everyone suspects that the missing relative holds the key to the family's story, the secret of where they came from and why they are as they are. The neutrino's mass is that missing guest, a presence implied but not yet revealed, a puzzle piece that refuses to fall into place. As you rest tonight, Imagine that gathering. Some relatives are loud and obvious, like the heavy quarks and bosons that dominate the conversation. Others are quieter but still clear, like the electron, familiar and reliable. And then, in the shadows, a faint figure waits, a relative who is part of the family but not yet fully seen. They do not raise their voice, but you sense that if they spoke, the entire room would fall silent, listening. That is the neutrino. Its mass is small, but its meaning may be immense. In the next session, we will step from theories of mass to the practical art of listening. We will descend into caverns filled with pure water, where vast detectors wait for faint flashes of blue, like fireflies flickering in the dark, each one a sign that a neutrino has brushed against the world of matter. Time equals 2 seconds. To study neutrinos is to accept that ordinary laboratories are not enough. A bench crowded with glassware, a chamber lined with wires, even a telescope pointed at the sky cannot capture particles that slip through matter as though it were fog. The search for neutrinos requires a different kind of imagination. It requires places as quiet and shielded as possible, built not on mountaintops but deep underground, where the Earth itself provides protection from the noisy hail of cosmic rays. There, in caverns carved from rock, scientists wait with vast pools of liquid, listening for flashes of light so faint that most of the time nothing at all seems to happen. Yet when it does, when a neutrino brushes against an atom, the silence is broken with a whisper of blue. Perhaps the most famous of these underground eyes is the Super Kamiokande detector in Japan, often called Super K for short. Imagine descending more than 1,000 meters into a mine, riding down in an elevator that creaks and hums until you emerge into a space so large it feels like the interior of a cathedral. Inside lies a tank filled with 50,000 tons of ultra-pure water. Lining the walls are thousands of photomultiplier tubes, each one an electronic eye ready to notice even a single photon of light. In the darkness of that chamber, most of the time there is only stillness. Billions of neutrinos stream through every second, leaving no mark. But every so often, one collides with an electron in the water, and when it does, something magical occurs. Because neutrinos interact through the weak force, the collision does not look like a bright spark or an obvious track. Instead, the struck electron is jolted into motion, moving faster than the speed of light in water. Not faster than light in vacuum, which is impossible, but faster than light can move through the medium of water. This creates a shockwave of light, a cone of bluish glow known as Cherenkov radiation. It is as though the electron becomes a miniature supersonic jet, leaving behind a light boom instead of a sound boom. The photomultiplier tubes capture this ring of light, and from its shape and timing scientists can reconstruct the neutrino story, its energy, its direction, sometimes even its flavour. The image of those faint rings glowing briefly in the stillness has become one of the icons of neutrino science. They look almost like halos, or the ripples of a pebble dropped into a pond, fragile circles that vanish as quickly as they appear. To those who work in Super K, each ring is a message from the invisible, proof that the ghosts of the universe can be coaxed into leaving traces. While Super K listens mostly for atmospheric and solar neutrinos, another experiment in Italy has been designed to hear the faintest whispers of the sun itself. This is Borexino, located deep beneath the Apennine Mountains in the Gran Sasso laboratory. Where Super K uses water, Borexino uses an extraordinary liquid, scintillator, a substance that releases tiny flashes of light when struck by a passing particle. The detector is shielded by layers of rock and tanks of water to keep out every stray signal except the ones that matter. Its sensitivity is astonishing, able to detect solar neutrinos of the lowest energies, the ones produced in the quietest nuclear reactions inside the Sun. The story of Borexino is not one of dramatic flashes but of subtlety. Its data comes not from obvious bursts, but from careful patterns, faint glimmers in the dark that must be separated from background noise with immense care. Yet those glimmers have told us that the sun is working exactly as predicted, that its quiet proton-proton chain of fusion reactions is steady and faithful, producing neutrinos that arrive at Earth without fail. It has confirmed, with exquisite delicacy, what had once been only theoretical models. To describe these detectors is to risk making them sound like machines, but to many who work in them, they feel more like living organisms, vast ears tuned to whispers, lungs breathing the silence of rock and water. The atmosphere inside is not one of loud discovery, but of reverence. Standing in the cavern of Super K surrounded by water and silence, one feels something akin to being in a cathedral, except the prayers here are not words but flashes of blue, and the congregation is made of ghost particles streaming from every corner of the cosmos. The firefly is perhaps the best analogy. Imagine yourself standing in a dark forest on a summer night. Around you the silence is thick, the trees loom and you can hardly see a thing. Then, in the distance, a faint flash of light appears, a firefly, then another, here and there, unpredictable but real. To catch a neutrino is like that. You cannot demand it, you cannot control when or where it will appear. You can only wait, surrounded by stillness, hoping for the flicker, and when it comes, for the briefest instant the darkness is punctured, and you know you are not alone. It is extraordinary to think that these faint flashes, these fragile rings of blue or tiny sparks in a tank of liquid, carry messages from the sun, from exploding stars, from the very processes that shape galaxies. They are fireflies of the universe, invisible to the naked eye but caught by the patience of human ingenuity. As you drift deeper into quiet tonight, imagine yourself descending into such a cavern. The air grows cooler, the noise of the world above fades. You step into a chamber filled with water so pure it seems unreal, surrounded by rows of silent electronic eyes. Most of the time, there is nothing to see. But then, now and again, the darkness blooms with a soft ring of light, as though a firefly has flashed deep underground. That ring is the footprint of a ghost, the sign that a neutrino has finally chosen to reveal itself. In the next session, we will travel from these caverns of water to the frozen expanse of Antarctica, where an observatory the size of a cubic kilometre listens for the highest energy neutrinos, messages from the most violent corners of the universe. If water-filled caverns beneath mountains can serve as ears for the universe, then ice itself can become a telescope. Not just any ice, but the ancient clear ice of Antarctica, layered and compacted over hundreds of thousands of years, frozen into crystalline silence. It is here, at the bottom of the world, that one of the largest observatories ever built stretches not upward toward the sky, but downward into the ground. It is called Ice Cube, and it is a telescope made not of glass lenses or metal mirrors, but of a cubic kilometre of frozen clarity. To understand Ice Cube, imagine a network of more than 5,000 sensors lowered deep into the ice, strung like beads along cables that sink 2.5 kilometres below the surface. Once frozen into place, each sensor waits in perfect darkness, surrounded by ice so pure that it has been untouched for ages. Above, the Antarctic surface is battered by winds and shifting snow. Below, silence reigns. The ice is not just cold, it is clean, a medium through which light can travel for extraordinary distances without scattering. In this frozen cathedral, even the faintest flashes can be seen. The principle is the same as in water detectors like Super Kamiokande. When a high-energy neutrino collides with an atom in the ice, it produces secondary particles that move faster than light can travel through that medium. They leave behind a cone of blue light, Cherenkov radiation, the same ghostly glow once seen in water tanks deep beneath mountains. In IceCube, however, the scale is far larger. A neutrino of immense energy can create a cascade of particles, lighting up strings of sensors across hundreds of meters. From the timing and brightness of those signals, scientists can reconstruct the neutrino's path, tracing it back across space to its source. The beauty of IceCube is in what it listens for. Deep beneath the ice, shielded from almost all interference, it is sensitive not only to solar neutrinos or atmospheric ones, but to the highest energy neutrinos nature can produce. These are born in the most violent events in the cosmos. The spinning maelstroms of black holes, the titanic jets of quasars, the cataclysmic explosions of gamma-ray bursts. Such neutrinos carry energies far beyond anything our accelerators on Earth can achieve, messages from natural laboratories more powerful than any human machine. In 2013, IceCube reported one of its first great triumphs: the detection of neutrinos so energetic they were named after playful cultural references, Bert and Ernie. Later detections traced neutrinos back to blazars, galaxies whose central black holes hurl jets of matter directly toward us at nearly the speed of light. For the first time, we had direct evidence that these extraordinary cosmic engines are capable of producing neutrinos, linking them to the century-old mystery of the origin of cosmic rays. It was as if the universe had whispered, through the medium of ghost particles, "Here is where the highest energies are born." Standing on the Antarctic surface, it is hard to imagine such messages passing beneath your feet. The winds bite, the horizon stretches flat and featureless, and the only sound is the crunch of boots on snow. Yet below, a vast telescope is watching in silence, catching flashes of blue light in the depths. The Earth itself becomes part of the detector. Neutrinos arriving from the northern sky travel through the entire planet before they emerge in the Antarctic ice, where IceCube waits. No other particle could do this. Photons would be absorbed, protons scattered, but neutrinos pass through almost untouched, carrying with them information from the farthest reaches of the cosmos. To detect them is to press your ear against the Earth and listen as the universe whispers through it. There is something quietly moving about the way IceCube transforms remoteness into clarity. Antarctica is among the most inhospitable places on Earth, a desert of ice and wind, yet in its depths lies one of our finest instruments for hearing the cosmos. The ice, once thought to be only an obstacle, becomes the very medium of sight. The world's coldest, quietest place becomes its most sensitive ear. The scale of the observatory is almost beyond imagination. A cubic kilometre of ice, 5,000 sensors, each one glowing faintly in the dark as it waits for a signal. Day after day, night after night, neutrinos stream through the Earth, most without interaction, but every so often one leaves behind a trace. Those traces, when pieced together, draw maps across the sky, pointing to galaxies, black holes, and cataclysms beyond our reach. The work is slow, the signals rare, but each one is a precious message from a part of the universe that no other messenger can reach. As you drift into rest, imagine lying beneath the Antarctic night. The sky above is filled with stars sharper than anywhere else on Earth. The air is so dry and cold it seems almost not to exist. Beneath you, kilometres of ancient ice stretch downward, silent and clear. Somewhere within that frozen cathedral, a neutrino has just collided, lighting up the darkness with a brief cone of blue. A ghost particle, born in the heart of a distant galaxy, has crossed billions of light years, passed through the Earth itself, and whispered its presence in a flash no wider than a blink. The ice has heard it, and now so have we. In the next session, we will turn from these triumphs of detection to the deeper question of why neutrinos are so hard to catch at all, why they escape us so easily, and what their indifference to matter tells us about their ghostly nature. After hearing of water caverns that glow with faint blue rings and Antarctic ice that turns into a telescope, it is natural to ask why such extraordinary measures are necessary at all. Why must detectors be so vast, so shielded, so patient? The answer lies not in human limitation, but in the nature of neutrinos themselves. They are built to escape. Their defining quality is indifference, a refusal to linger with matter, a determination to pass through almost everything as though it were not there. Neutrinos are electrically neutral. Unlike electrons or protons, they do not feel the electromagnetic force. They carry no charge, and so they do not bend in magnetic fields or spark in detectors designed for charged particles. They also ignore the strong nuclear force, the force that glues protons and neutrons together in atomic nuclei. What remains is the weakest of all interactions, fittingly called the weak force, and gravity, which at the scale of particles is too feeble to matter. That is all neutrinos will acknowledge. To interact with a neutrino, the universe must rely on the weak force alone, and the weak force lives up to its name. The result is astonishing. Every second, about 100 trillion neutrinos pass through your body. They flow through your skin, your bones, the earth beneath your feet, the oceans and the mountains without pause or hindrance. In the time it takes to draw a breath, more neutrinos have passed through you than there are grains of sand on all the beaches of the world. And yet, in all those countless crossings, not one has likely left the slightest trace. If you wished to stop just half of them, you would need to build a wall of solid lead 1 light year thick. Even then, the other half would still emerge on the far side, untouched, unbothered, still moving forward as though the wall had never existed. This is why neutrino experiments must be so immense. If the odds of a neutrino interacting are so vanishingly small, the only way to catch them is to wait with vast volumes of material, giving the ghosts as much opportunity as possible to leave a mark. It is like trying to catch raindrops with a net made of chicken wire. Most drops will pass through, falling freely, but if the storm is heavy enough and the net is wide enough, now and then a drop will strike the wire and cling. The detectors are our nets, stretched across the flood of neutrinos, waiting for rare collisions that confirm the invisible as brushed against the tangible. The scale of their indifference can be difficult to imagine. Photons, those nimble messengers of light, are constantly interacting with matter. They bounce from mirrors, scattering clouds, warm your skin, and paint your vision with colour. Neutrinos, by contrast, behave as if the world were transparent glass. A neutrino born in the core of the sun slips out in seconds, while a photon may wander for 1,000,000 years. A neutrino from a distant galaxy can cross billions of light years, through stars and planets and nebulae, and still arrive unchanged. They are the great escape artists of the cosmos, refusing to be stopped, and yet this very slipperiness is what makes them precious. Because they are not easily scattered, they carry information unblurred by the matter they pass through. They tell us what is happening in the densest regions, in the cores of stars, in the first second of the universe itself. They are both frustrating and invaluable. Frustrating because they are so hard to catch. Invaluable because if you do catch one, it speaks with an honesty no photon can match. Physicists sometimes talk about the neutrino's cross-section, a technical term that measures how likely it is to interact. For most particles, the cross-section is like a doorway through which collisions can happen. For neutrinos, the doorway so small it is almost not there at all. But almost not there is not the same as never. That sliver of possibility is enough. With tanks of water, pools of scintillator, cubic kilometres of ice, and decades of patience, we can gather the few rare encounters and stitch them into a story. There is something humbling about this pursuit. We build detectors the size of cathedrals, bury them in mountains, sink them beneath oceans of rock, and still the neutrinos pass through, mostly unacknowledged. The Earth itself is transparent to them, the planet no more an obstacle than a wisp of smoke. We, with all our ingenuity, must accept their aloofness. But in that acceptance lies a kind of peace. To study neutrinos is to learn patience, to understand that not all truths come easily, that some require listening for whispers in a storm. As you drift tonight, picture yourself standing in the rain with a net of chicken wire. Drop after drop passes through, unstoppable, invisible. You feel almost nothing. But then, just once, a single drop clings to the wire. In that tiny moment of success, you know that the storm is real, that the flood is there. Even if most of it escapes you, that's what it means to catch a neutrino. Most slip by, but the rare ones that pause tell us of suns, of galaxies, of the universe's first heartbeat. In the next session, we will leave the silence of caverns and ice and travel to the sky itself, where neutrinos serve not only as curiosities but as messengers. We will see how they announce the death of a star before light could reach us, and how they may one day allow us to hear the universe's grandest symphony in full. In February of 1987, astronomers watching the skies were given a rare gift. In the Large Magellanic Cloud, a small neighbouring galaxy about 160,000 light-years away, a star reached the end of its life in spectacular fashion. Its core collapsed, its outer layers exploded outward, and a new light flared in the heavens. It was the brightest supernova visible from Earth in nearly 4 centuries. People around the world turned their telescopes to the southern sky, watching as a faint point of light swelled into a beacon, a reminder that stars are not eternal but live, die, and seed the cosmos with their remains. The event became known simply as Supernova 1987A. What most people did not know at the time was that the first messengers from this cosmic death had not been photons. They had not been particles of light racing across the void, carrying the image of a star undone. They had been neutrinos. When a massive star collapses, the violence begins in its core. The crushing gravity forces protons and electrons to merge into neutrons, releasing an immense flood of neutrinos in the process. These ghostly particles escape immediately, passing through the stellar envelope with hardly a pause. Light, by contrast, is delayed, trapped by dense layers of matter until the shockwave pushes them outward. For SN 1987A, this meant that the neutrinos arrived on Earth hours before the photons. It was as though the universe had whispered the news of the star's death before unveiling it to the eye. At the time, only a handful of detectors in the world were capable of catching such events. In Japan, the Kamiokande detector, the predecessor to Super Kamiokande, was buried deep in a mine, its tank of water waiting for flashes of Cherenkov light. In the United States, the IMB detector in Ohio kept a similar vigil. A smaller instrument in Russia, the Baksan Neutrino Observatory, also listened in the dark. When the flood of neutrinos from the collapsing star swept across Earth, each detector stirred with activity. In Kamiokande, a dozen neutrinos revealed themselves. In IMB, a few more. In Baksan, a handful. Altogether, fewer than 30 neutrinos were recorded. It may sound like almost nothing, a paltry harvest compared to the trillions streaming through us every second. But those 24 neutrinos carried with them the story of a star's final breath. They confirmed that supernovae release their energy not primarily in light, but in neutrinos. In fact, more than 99% of the energy of a collapsing star is carried away by neutrinos, a torrent so immense that for a few seconds, the dying star outshines the rest of its galaxy in neutrinos alone. For physicists, the detections of 1987 were electrifying. They had waited decades for such an event, knowing that only a nearby supernova could produce a signal strong enough for our primitive detectors. The timing, the energies, the arrival before the light, all matched the theory. In those few hours, neutrino astronomy was born. No longer were neutrinos just curiosities to be hunted underground or in ice. They were cosmic messengers, carrying urgent news from the heart of stars in their last moments. There is something haunting about the thought. When the neutrinos of SN 1987A were created, the Earth was still in the midst of the last ice age. Human beings had not yet written words. Civilizations would rise and fall before those neutrinos completed their journey across space. And then, one February night, they arrived, brushed through our detectors, and vanished again, leaving only faint flashes to mark their passing. Hours later, the light followed, and the world saw the star explode. But the whisper had already come. To stand in a detector as those neutrinos arrived would not have been dramatic. There would have been no blinding glow, no roar of activity. Only a series of small signals, a few dots of light against the dark, quiet as fireflies in a cavern. And yet, in those dots was the voice of a star collapsing, a whisper that crossed the cosmos to say, "I am gone." The detection of SN 1987A's neutrinos gave confidence that we could, with enough patience, listen to the universe in this new way. It proved that neutrinos could arrive first, carrying warnings before light breaks free. It showed that in the death of stars, the ghosts not silent but shout with invisible energy. And it reminded us that even the rarest signals, a handful of particles in tanks of water, can reveal truths larger than galaxies. As you let your mind quiet tonight, imagine the journey of those neutrinos. They streamed from the heart of a collapsing star, slipped past layers of burning matter, crossed the void for 160,000 years, and then passed through you, through me, through mountains and oceans, on their way to detectors that waited patiently underground. They didn't pause, but for a brief instant they left behind a trace, a sign that they had been here. And then they were gone again, already travelling onward. In the next session we will look at another event, one far more recent, where the universe gave us a different kind of message. A merger of neutron stars that shook space itself was seen in light across the spectrum, but left us waiting for neutrinos that never arrived. In August of 2017, the universe offered us another message, one unlike any before. Astronomers and physicists around the world had been waiting for it for decades, watching instruments that stretched across continents, hoping for the moment when two different messengers would arrive together. That moment came when a ripple passed through space itself, a shudder of the fabric of reality that swept across the Earth, faint yet unmistakable. The gravitational wave detectors LIGO and Virgo, built with almost impossible precision, recorded the signal within seconds. It was the first clear detection of a collision between two neutron stars. Neutron stars are themselves remnants of supernovae, cores of stars so dense that a spoonful would weigh as much as a mountain. To imagine two of them spiralling together is to imagine a dance of extreme gravity, each star tearing at the other with tides stronger than anything on Earth. As they circle closer and closer, their orbit quickens, until at last they collide in a burst of energy so violent that it rattles space-time itself. The signal that reached Earth was a chirp, a rising tone in the detectors, lasting just over a minute. From it, physicists knew that two neutron stars, each heavier than our Sun but only the size of a city, had merged in a galaxy 130 million light-years away. Almost immediately, telescopes across the world turned toward the patch of sky from which the wave had come, and this time, unlike earlier gravitational wave detections, there was light as well. Across the spectrum from gamma rays to radio waves, astronomers watched as the afterglow of the merger blossomed. They saw the creation of heavy elements, gold, platinum, uranium, forged in the violent kilonova, scattered across space to become part of future planets, perhaps even future jewellery or coins. It was the first time the cosmos had given us such a performance, with both the deep bass of gravity and the shimmering treble of light playing in harmony. And yet, one expected instrument was missing. No neutrinos were detected. For months, scientists scoured the data from neutrino observatories around the world. Super Kamiokande in Japan, IceCube in Antarctica, detectors in Europe and North America. They found nothing. Billions upon billions of neutrinos must surely have been produced in that titanic collision, but if they were, they slipped past us without a trace. The orchestra had played without its ghostly section, leaving the music both beautiful and incomplete. Why did neutrinos not arrive? Perhaps they were produced, but at energies or directions that our instruments could not register. Perhaps the merger, different from a supernova, did not release them in the same way. Or perhaps they were there in such small numbers that the detectors, limited in sensitivity, were simply too deaf to hear. Whatever the reason, their silence was itself a reminder of how difficult it is to listen to the universe in full. Even with our greatest instruments, much of the cosmic symphony remains beyond reach. The absence of neutrinos in 2017 did not diminish the wonder of the event. On the contrary, it showed how far we had come. For the first time, astronomers could point to a single cosmic cataclysm and say they had heard it in gravity, seen it in light, and searched for it in ghosts. It was the dawn of what is now called multi-messenger astronomy, the joining of different kinds of signals into a fuller picture of the universe. We were no longer listening to only one voice at a time, but beginning to hear the choir. The missing neutrinos were like an empty chair at a performance, a reminder that the ensemble is not yet complete. And still, there was beauty in that silence. It left us with anticipation. Somewhere in the future another merger will occur, another burst will send out gravitational waves, light, and, perhaps this time, neutrinos. The next event may give us the full orchestra, every instrument together, a cosmic symphony that speaks across all messengers. As you rest tonight, imagine that merger. Two neutron stars circling each other, faster and faster, spiralling inward, their surfaces glowing, their magnetic fields twisting. The moment of collision sends ripples through space-time, shakes the universe like a drum, and lights up the sky in colours no eye has ever seen directly. You feel the deep bass of gravity first, then the shimmering chorus of photons. You wait for the ghosts to join, but they remain silent, leaving you with an unfinished harmony. It is not a disappointment, but an invitation to keep listening, to keep building instruments, to keep waiting for the day when the universe plays the whole song. In the next session, we will turn from individual events to the broader vision of multi-messenger astronomy itself. We will think of it as an orchestra, in which light, gravity and neutrinos each play their parts. Some instruments are already heard, others remain faint, but together they promise a music far richer than any single voice could ever give. When people speak of astronomy, they often think first of light. For thousands of years it was all we had. Starlight guided sailors across oceans, traced the seasons on calendars carved in stone, and painted the heavens with myths. Even now, with telescopes of unimaginable size, we remain creatures of light, trained to see the universe in photons across every wavelength, from radio to gamma rays. But light is only one instrument in a far larger ensemble. The 20th century taught us to hear more. In 2015, we first learned to listen to the bass notes of gravitational waves, deep tremors in space-time itself, produced when massive objects collide. In 1987, we discovered that neutrinos, those elusive ghosts, can carry whispers from the collapsing hearts of stars. Each messenger tells a different story. Light reveals surfaces, gravity reveals motions, neutrinos reveal interiors. Alone, each is powerful. Together, they are music. This idea is called multi-messenger astronomy, and it is like standing at the back of a concert hall as more and more instruments join in. At first, you hear only a single violin, thin but clear. Then a cello enters, grounding the sound. Then a trumpet brightens it. A drum deepens it. Piece by piece, what was once a solo becomes a symphony. The universe has always played this music, but only now have we begun to hear it in full. Think again of supernova 1987A. The neutrinos arrived first, carrying the intimate news of a core collapsing into neutron-rich matter. Hours later, the light came, unveiling the spectacle to telescopes. For that brief moment, we had two instruments in the orchestra, ghosts and photons. 30 years later, in 2017, the neutron-star merger gave us gravity and light together. Again, two instruments, but this time a different pairing. The deep rumble of space-time and the shimmering tones of electromagnetic radiation. Both events were incomplete, one missing gravity, the other missing neutrinos. Yet taken together, they were enough to convince us of the music waiting just beyond our reach. Multi-messenger astronomy is still young, its score barely unfolding, but its promise is immense. Imagine the next great stellar collapse caught not only in photons but in gravitational waves and neutrinos as well. Imagine a killer nova whose story is told not only in the glow of new elements, but in the ghosts that slip away and the ripples that shake space-time. Such an event would be a concert, every instrument present, every voice heard, a harmony richer than anything light alone could give. What makes this vision soothing is not only its scientific promise, but its reminder of wholeness. No single sense is ever enough. Sight without sound leaves us blind to music. Sound without sight leaves us unaware of colour. In the same way, astronomy without neutrinos or gravity leaves us with an incomplete portrait of the cosmos. The universe is generous, but it does not give its secrets easily. It asks us to gather every tool, to open every ear, to notice every whisper. Only then does the choir reveal itself. Even now the metaphors come easily. Light is the treble, quick and bright, carrying melodies across the void. Gravitational waves are the bass, slow and resonant, carrying the rhythm of mass in motion. Neutrinos are the altos and tenors, subtle, weaving between, telling of what lies hidden behind curtains. Without them, the harmony is thin. With them, the sound deepens into something almost spiritual. One day, perhaps, we will hear the full choir. Our detectors will be sensitive enough to catch neutrinos from every kind of cataclysm, not only the rare nearby supernovae. Gravitational wave observatories will expand their reach, hearing colliding black holes and neutron stars across the whole universe. Telescopes, freed from Earth's atmosphere, will span every wavelength, from the coldest radio hum to the hottest gamma flash. Then, when the next great cosmic event unfolds, we will hear it in full surround, a harmony of light, gravity and ghosts, joined by instruments we have not even imagined yet. As you drift towards sleep, imagine standing in a great darkened hall. At first, there is only silence. Then a violin begins, thin and lovely. After a time, a drum joins, low and steady. Then another voice, faint but resonant, enters the space. The music thickens, grows richer, becomes something larger than any single sound. That is the universe we are beginning to hear. We are learning to step into its concert, to listen with every sense we can build, to take the fragments and weave them into a symphony. In the next session, we will leave these modern concerts and travel backward in time to the universe's earliest moments. We will see how light itself was once trapped, unable to reach us, and how only neutrinos, the ghosts, slipped free in the first second. Their message has been travelling ever since, waiting for us to learn how to listen. When we look far into the depths of space with our best telescopes, what we see is not only distance but time. Every patch of sky is a time machine. Light travels at a fixed speed, and so the farther away a galaxy is, the longer its photons have been in transit. Look far enough, and you glimpse the universe as it was billions of years ago. Yet even this reach has a limit, and the boundary is written in the nature of light itself. The universe began hot, dense, and filled with a plasma of protons, electrons, and photons all tangled together. In those first moments, light could not travel freely. Every photon was trapped, scattering constantly off charged particles, bouncing and ricocheting in a fog so thick that transparency was impossible. Imagine trying to see across a room filled with steam so dense you could hardly make out your own hand. That was the cosmos in its infancy. For nearly 400,000 years, the universe glowed but could not be seen, luminous yet opaque, its light imprisoned in a restless dance with matter. It was only when the universe cooled enough for protons and electrons to join into neutral atoms that this fog lifted. At last, photons were freed to stream across space without constant scattering. This great release is what we call the cosmic microwave background, the CMB, the oldest light we can observe. Captured by satellites and telescopes, it appears as a faint glow across the entire sky. A baby photo of the universe taken 380,000 years after its birth. It is beautiful, rich with patterns, but it is also a reminder of how late light arrived. If all we had were photons, our vision of the universe's childhood would stop there, at those first few 100,000 years. Everything before remains hidden, veiled in opacity. The first second, the first minute, the first hour, all of them lie beyond light's horizon. We know they happened, we can infer their story from the particles and forces we see today, but we cannot look at them directly with photons. The window of light is closed to those earliest moments. Neutrinos, however, tell a different story. Unlike photons, they do not scatter easily. They do not cling to charged particles or ricochet endlessly in a dense plasma. They are aloof, almost indifferent, and in that indifference lies their gift. Within the first second after the Big Bang, when the universe was still a seething soup of particles, neutrinos were already slipping free. They decoupled, as physicists say, streaming outward unimpeded, carrying with them a record of conditions at that earliest moment. They are not delayed for centuries of thousands of years. They are not blurred by fog. They left almost immediately, and their journey has continued unbroken for more than 13 billion years. Imagine the contrast. The light we see from the CMB is like a photograph developed long after the moment was taken, finally visible when the fog cleared. The neutrinos, by contrast, are like eyewitnesses who slipped out of the crowd in the very first seconds, carrying their story straight through to us. If only we could capture them, we would see not just the baby face of the universe, but its first breath, its earliest heartbeat, its raw beginning. This difference is not only poetic but practical. The CMB reveals the universe as a child of hundreds of thousands of years. It shows us the seeds of galaxies and the tiny fluctuations of temperature across the sky, ripples that later grew into clusters of stars. But the neutrinos could show us what happened before those seeds were planted, before matter settled into its current forms, when everything was still in flux. They could tell us about conditions at 1 second, a time when the temperature of the cosmos was 10 billion degrees, when protons and neutrons were forming, the atoms themselves were being set in place. Even without catching them directly, scientists can see faint echoes of this early neutrino flood. Their presence is imprinted in the very patterns of the cosmic microwave background, and in the way galaxies cluster across space. Just as the wind leaves ripples in sand long after it has passed, so too do relic neutrinos leave ripples in the cosmic structure, subtle but measurable. These traces reassure us that the neutrinos were there, that they streamed free in the first second, even if their direct voices remain unheard. And so we stand in a curious position. With light, we can see the universe back to its 380,000-year-old self, wrapped in cosmic infancy. With theory, we can reconstruct what likely happened before, but with neutrinos, if we could only capture them, we would hear the universe speaking in its first instant, a message older than any light. It is as if we are looking at a family album and see the baby photos, But we know that somewhere, perhaps lost in a drawer, is a recording of the child's very first cry. We cannot hear it yet, but we know it exists. As you settle deeper into quiet tonight, imagine that foggy universe, dense and hot, photons trapped in endless collisions, unable to escape. Then imagine the neutrinos, slipping through that chaos like shadows through mist, leaving behind the first and truest record of what the cosmos was becoming. Those same neutrinos are still around you now, drifting silently, countless in number, as old as time itself. They are the ghosts of the first second, brushing through you without pause, reminders that the universe has always had more to say than light alone can tell. In the next session, we will explore what scientists call the cosmic neutrino background, the relic sea of neutrinos left over from that first second. We will see how cold and faint it must be today, how it has left its fingerprints on the structure of the cosmos, and why capturing even a single one of those ancient ghosts would be like touching the universe's first breath. If the cosmic microwave background is the baby picture of the universe, then the cosmic neutrino background is something even older, a record not from hundreds of thousands of years after the beginning, but from the very first second itself. It is the faint afterglow of the moment when neutrinos decoupled, slipping free from the hot plasma and travelling ever since, untouched, unchanged, silent witnesses to the dawn of time. Today, more than 13 billion years later, they are still here, filling every corner of space, brushing through galaxies, planets, oceans, and people, an invisible sea that none of us can feel. Physicists call it the C-nu-b, shorthand for the cosmic neutrino background. If you could somehow see it, it would not dazzle like the microwave background, which still glows across the sky. It would not paint a picture you could frame. It would be quieter, colder, subtler. Over the eons, the expansion of the universe has stretched their energies thinner and thinner, slowing them until their average temperature is only about 1.95 Kelvin. That is just 2 degrees above absolute zero, colder even than the microwave background itself. These relic neutrinos drift not as racing ghosts, but as a chilled fog, a background presence that suffuses all of space. Though we cannot yet detect them directly, their fingerprints are everywhere. The CMB left delicate marks on the cosmic microwave background, altering the way the early plasma rippled before photons were released. Imagine a pond in winter. The surface freezes, and ripples are locked in place, preserved as patterns in the ice. When you look at the frozen pond later, you can tell that waves once danced there, even though the water no longer moves. The cosmic neutrino background left ripples like that, frozen into the CMB's subtle patterns. We see them in the statistical swirls of temperature across the sky, clues that neutrinos streamed free when the universe was only a heartbeat old. They have also left their imprint on the large-scale structure of the cosmos. Because neutrinos are so numerous, their collective mass influences how galaxies form and cluster. Imagine dust gathering into piles. If there is a constant invisible breeze, the piles will form differently, spread wider, smoothed at the edges. Neutrinos, light as they are, act like that breeze. Their presence in the early universe suppressed the growth of small-scale structures, smoothing the cosmic web in ways we can still measure. When cosmologists map the distribution of galaxies across billions of light years, they can trace the hand of relic neutrinos in the delicate patterns of clustering. And so, even without holding one directly in our instruments, we are confident that the CNB is real. It is one of those invisible presences that makes itself known through its effects, like a hidden current felt in the drift of leaves, or the pressure of air unseen yet undeniable in the sway of trees. The relic neutrinos are here, a sea we swim in constantly, though we have not yet learned how to cup our hands and gather even a single drop. To detect them directly is one of the great dreams of physics. Experiments such as Ptolemy, planned in Italy, hope to capture relic neutrinos by watching for the rarest of interactions with tritium atoms. If successful, the experiment might record just a handful of events each year, perhaps even one every few years. The patience required is immense. To wait for such a signal is like waiting beside a dry stone well, listening for the sound of a single drop of water falling in the darkness, knowing it might take decades to arrive. But even one confirmed detection would be revolutionary. It would be the oldest message humanity has ever held in its hands, a direct touch of the first second of time. There is a certain comfort in knowing that such signals exist, even if they are beyond our reach for now. The universe has not hidden its first moments entirely. It has left records for us to find. The photons of the cosmic microwave background are one kind of record. The neutrinos of the C&B are another, and together they form a layered archive of cosmic memory. We are archivists learning how to read, piecing together pages scattered across billions of years, slowly reconstructing the story of our origins. As you rest tonight, imagine yourself standing at the edge of a frozen pond. The surface is still, silent, and cold. Yet when you look closely, you see faint ridges in the ice, patterns left behind by ripples long ago. The water does not move now, but you know it once danced. That is what the cosmic neutrino background is to us. Ripples frozen in the fabric of the universe, proof that the ghosts once flowed freely, leaving behind marks we can still trace. In the next session, we will turn to the almost impossible patience required to catch these relic neutrinos directly. We will meet the experiments that hope to do so, experiments that may wait decades for a single event, and we will imagine what it would mean to finally hear a raindrop that has been falling since the universe's first second. For scientists, knowing that relic neutrinos exist is both exhilarating and frustrating. They are certain the cosmic neutrino background must be there, a sea of ghosts drifting at just under 2 degrees above absolute zero, older than the oldest light. Its fingerprints are visible in the ripples of the cosmic microwave background, and in the patterns of galaxies across space. The case is airtight. And yet, there remains the longing for direct proof, the desire to catch one in the act, to hold a single relic neutrino in the net of an experiment and say, here it is, a survivor from the universe's first second. That longing has inspired projects like PTOLEMY, an experiment planned with extraordinary delicacy and almost impossible patience. The principle is deceptively simple. Place a thin film of tritium, a heavy form of hydrogen, under watch. Tritium naturally undergoes beta decay, releasing electrons and antineutrinos. But if a relic neutrino from the background collides with a tritium atom, it can trigger a reaction that produces an electron at a slightly different energy, a tiny deviation from the expected pattern. Detect that one subtle shift, and you have caught the ghost. The challenge is not the principle, but the scale. The flux of relic neutrinos is immense. They fill every cubic centimetre of space, but their energy is vanishingly small, their interactions rarer still. Ptolemy might expect to see only a handful of such captures in a year, perhaps even just one. Imagine waiting at the edge of a dry well, straining to hear the sound of a single drop of water. Days pass, weeks, months, and the silence stretches on. You know the drop must come eventually, but you cannot predict when. That is the patience relic neutrino detection demands. It is a patience matched only by the ambition of what success would mean. To catch even one relic neutrino directly would be to touch the universe as it was in its first second, not inferred, not traced in ripples, but felt in a single event recorded in an earthly laboratory. It would be like finding a fossil from the first heartbeat of time, holding it in your hand, and knowing that it has travelled unbroken across 13 billion years to meet you. The detectors must be exquisitely sensitive. Every electron released in decay must be measured with near-perfect accuracy. Every background signal must be silenced, every stray vibration or fluctuation accounted for. It is less like building a machine and more like cultivating a sanctuary, a place so quiet that even the faintest whisper can be heard. The people who design such experiments are not only engineers or physicists, but custodians of stillness, guardians of patience, waiting for a message that may come once in decades. In a way, this is the essence of neutrino science itself. Always the particle asks us to be patient, to build vast tanks of water or ice, to wait in caverns for fireflies of light, to measure shadows in cosmic ripples. Ptolemy carries this tradition to its limit, asking us to wait not just for ordinary neutrinos, but for the oldest ones, the ones that carry the memory of the very first second. The experiment's name, borrowed from the ancient astronomer who mapped the stars, feels fitting. Ptolemy charted the heavens with patient geometry, trusting patterns invisible to the naked eye. Ptolemy. The experiment seeks to do the same, tracing ghosts older than any star, mapping the very beginning of time. The rarity of the expected signal has a strange poetry. In a world filled with constant noise, endless messages and images and alarms, here is an experiment that listens for one event in years. A single click, a single deviation in energy, would be enough to announce that the oldest messengers of all have finally spoken. It is the opposite of haste. It is science in its slowest and most contemplative form. As you lie in stillness, consider how much meaning can rest in a single drop. The relic neutrinos are everywhere, countless beyond counting, yet our ability to sense them is so limited that we may celebrate for decades over one confirmed detection. It is a reminder that significance is not always measured in abundance. Sometimes the rarest signal, the quietest event, holds the greatest truth. Imagine waiting in a vast hall for the sound of a raindrop. The roof is high, the silence is deep, and time stretches endlessly. Then, at last, a drop falls, ringing in the stillness like a bell. That single sound is enough to prove the rain exists, even if the storm remains unseen. So it will be with a Ptolemy, if it succeeds. One event will be enough to tell us that the ghosts of the first second are not only real in theory, but present in our instruments, here with us, whispering still. In the next session, we will leave these patient experiments and reflect on what neutrinos in all their elusiveness have taught us. We will gather their roles as messengers, as puzzles, as quiet shapers of galaxies, and see how they remind us of the universe's tendency to hide its truths in whispers rather than shouts. Through all these nights of listening, we have followed neutrinos from their hesitant invention in a letter to their first fleeting capture in a cavern, from the puzzles of the sun to the great detectors of water, ice and rock. We have seen them appear as actors in supernova, vanish in mergers, and leave their frozen imprints on the very shape of the universe. Again and again, they remind us that the most elusive messengers can also be the most revealing. Their story is not one of noise and spectacle, but of whispers that carry truths no other particle can tell. Neutrinos are probes, slipping through walls that stop every other signal. They tell us what is happening inside the sun, not in the long-delayed light, but in the instant now. They warn us of stars collapsing before photons have escaped. They travel across galaxies, ignoring obstacles, carrying to us news of cataclysms we would otherwise never know. They are time travelers of a kind, not because they defy the arrow of time, but because they show us events at their very core, events hidden from every other messenger. But neutrinos are also puzzles. Their masses, tiny yet real, defy the neatness of the standard model. Their flavors oscillate like dancers swapping masks, making them both familiar and disguised. Their hierarchy remains uncertain, their exact weights unknown, their origins of mass still mysterious. Perhaps they carry secrets about why matter itself exists, why the universe did not annihilate itself in the first moments. Perhaps sterile neutrinos, if they exist, explain the hidden matter that binds galaxies together. Again and again, neutrinos stand at the border of what we know and what we do not. What makes their story soothing to hold is the way it mirrors our own search for meaning. We too are often blind to what is around us, seeing only fragments, missing entire dimensions of truth. We too live among illusions, with brains that smooth and buffer reality, painting sunsets orange, compressing moments of fear into slow motion, stretching boredom into endless minutes. Yet just as we build telescopes to borrow new senses, we build ideas to reach beyond our illusions. Neutrinos, in their silence, remind us that reality is always deeper than it appears, always carrying whispers beneath the noise. If one day we capture relic neutrinos directly, if Ptolemy or some future experiment hears that single raindrop in decades of silence, it will not only confirm the cosmic neutrino background, it will confirm that patience itself is part of science, that waiting and listening are as important as building and discovering. That one event would be like touching the universe's first breath, holding in our hands a memory older than light, older than any photograph, older than any galaxy. And yet, even without that final triumph, neutrinos have already given us so much. They have shown us that mass is not always heavy, that importance is not always obvious, that sometimes the tiniest things shape the largest structures. They have humbled us, reminding us that our great detectors, vast as they are, catch only the rarest traces while billions upon billions pass unnoticed. They have taught us to reimagine what it means to observe, to accept that absence itself can be information, that silence can speak. Perhaps that is the truest gift of neutrinos. They are ghosts that slip through everything, indifferent to our bodies, our planet, our instruments, and yet they leave wisdom behind. They are both present and absent, both elusive and essential, both frustrating and profound. To think of them is to be reminded that the universe does not always shout its secrets. More often it whispers, and it is up to us to quiet ourselves enough to hear. As this journey closes, imagine yourself surrounded by that invisible sea of neutrinos. They pass through you constantly, in numbers beyond imagination, silent and unstoppable. You feel nothing, yet they are there, like the slow breath of the cosmos, brushing through everything, carrying with them the memory of stars, of galaxies, of the very first second of time. If you drift into sleep now, think of those ghosts not as cold or distant, but as companions, reminders that the universe is full of stories too quiet for ordinary senses, yet waiting for those willing to listen. And so, we reach the quiet end of tonight's journey. Thank you for sharing this time, for letting these whispers of physics accompany you into rest. The ghosts may slip through us without pause, but they leave behind meaning, and perhaps even comfort. Sleep peacefully under the endless chorus of neutrinos that have been singing since the beginning.